Hello everyone, welcome to this new course on Hands-on CFD. So I am Sumant Morav. I am a PhD graduate from Indian Institute of Technology, Bombay. So coming to the motivation behind this course, so there are several courses on CFD which you can find on YouTube, and also CFD course is like one of the main elective which is provided in I think almost every university in at least mechanical and aerospace department. So there is already a lot of material available online as well as in university wherever you are studying, but as the name indicates, so we want to work mainly on hands-on CFD, that is coding aspect, which is most of the time not considered in the curriculum. So mostly people either go with the commercial computational fluid dynamics tool which is available, and many a times a theoretical background is given, but the difficulties which students face with coding is not dealt with. That is what I felt, and that is why I have come up with this course. Okay, and I had got some what do you say, motivation from a student side as well. Some of the students had actually messaged me saying that it would be great if we could have some kind of coding videos for computational fluid dynamics. So that was the main motivation, and also the second big motivation is that I would also like to introduce some of the new trends which are coming up in computational fluid dynamics. So that's the second thing. So the way in which this course would work is that I would not go too much deep into the theoretical aspects, because for that you can go through some already available resources. Okay, textbooks or the online resources, something like that. Or else I have actually made two different playlists for that, wherein I have dealt mostly with theoretical aspects. You can go through those videos also. Okay, so I will just briefly touch upon the theoretical aspect, and I will directly go into the coding aspect. How do you convert this knowledge into a practical tool or a code? Okay, so that's the main thing. And again, we won't be using any commercial softwares here, so that's not going to be the approach. So that's about this course. Now coming to the first lecture, which for which there was a demand, so that is why I have started with this. So it's the computational heat conduction, and so mainly I will be dealing with the finite difference method, which is the simplest method, I would say. So let us start from the simplest method. In between, we will switch to finite volume method also, because that is more robust. That you will come to know anyways on the way. So yeah, so let's begin this course. So first, before getting into computational heat conduction, so we have to understand what are the three aspects through which, by gaining the knowledge of which, you can become a good CFD engineer. So the first thing, which is very obvious, is the knowledge of basic fluid mechanics and heat transfer. That is very essential. Okay, to be, to become good at CFD, I would say. So the second thing is, okay, when you know basic fluid mechanics and heat transfer, you will be knowing the equations which you have to solve. You will be knowing the physical models. So those equations, the set of equations are called as physical models. So you know how to solve those physical models, but those physical models are mostly in partial differential equations, and you have to know how to convert those partial differential equations into algebraic equations, and only then you can solve them. Okay, it's very difficult to solve directly a partial differential equation through some numerical ways. Okay, for the computer to solve it, it will be difficult. So that is what I am telling, because ultimately we want to solve these things through a computer, right? And not only how to convert these PDEs into algebraic equation, but you also have to know, okay, once I get the algebraic equations, how do I exactly go about solving those, solution methodology. Okay, so these are two things which you have to kind of know. And uh, the second thing I will be going through in this course. So as of now, if you don't know, that's fine. But what I want you to know is at least the basic fluid mechanics and heat transfer. That is one, I would say, a prerequisite. Okay. Now the third thing which is necessary in today's world, this might have not been necessary 10 years ago or even 5 years ago, but now it's necessary. So there is a lot of integration of computational fluid dynamics with machine learning techniques. So the main drawback of CFD, I would say, is, see, you will be able to do, I mean, if you set up the experiment, say for flow in a tube with some droplets being injected there, okay. So that kind of experiment you will be able to do in something like seconds or even say minutes. Okay, the experiment will be done, and you can do multiple repetition of those things. Okay, within 1 hour you can do the experiments. Okay, so the physical time will be very less. That is like 1 minute, 2 minute of experimental time. But to do the same 1 minute time through computational fluid dynamics, it will take days. Okay, to the traditional, I am talking with respect to the traditional CFD approach. It will take days. Now, how do we optimize this? This is the main question. And really, to some aspects, machine learning has answered these questions. And also, machine learning is helping CFD in other aspects also. In some of the physical models, we do not have a very close models. For example, in turbines, okay, the Reynolds average Navier-Stokes equations, wherein you have Reynolds stress. We have some models which were derived through some data which was existing. Okay, some empirical models. You have those things, and we try to solve it using those approaches. But really, machine learning, once it has some data of experiments, at least at a very minor level, if there is some data which is usually available, okay, it can come up with its own physical models, I mean, which are slightly different from what we have, and maybe we couldn't have guessed them. So those kind of things are possible. So that's the second main advantage, I would say, of machine learning. And now wherever you see in the internet, you will see such pictures. This is again generated from AI algorithm, and this is not very accurate representation of contour or this thing space shuttle, but yeah, it's still in the preliminary stage, so you can expect it to become better and better as the time goes on. And definitely we would be able to take a lot of advantage of computational fluid dynamics. So one of the main trending topic in this ML with computational fluid dynamics is the physics informed neural network. So the neural network tries to do some kind of regression and gives you the answer, but how do you know whether it is correct or not? So in physics informed neural networks, we try to test it with the governing equation. So it's like you calculate some answer and put it in the governing equation and just check whether it is being satisfied or not. Okay, so there is a lot of advantage with that kind of calculation also, but I will go into those things at the end of this course. Okay, not in the beginning. So in the beginning we will deal with very simple equations, how to solve them, computational heat conduction, computational heat advection, and then we will take up Navier-Stokes equation, how to solve them. Once we are comfortable with that, we can try to see what are the trends in machine learning, all those things. Okay, okay, so that I think is good enough for the introduction. So, so the first lecture, as I said, will be on 2D computational heat conduction, unsteady state, solving it in an unsteady state. So, I think you might be a bit acquainted with these terms, so I will not go into very depth. So, we have an unsteady flow, which means that the variable, the velocity or the temperature, whatever it is, here it's the temperature, it's varying with respect to time. Okay, it doesn't reach a steady state. That is why unsteady. Okay, so we are taking just a conduction here. We are ignoring the advection. We are assuming that there is no velocity which is involved. It's a stagnant condition. So we get these equations. Now, as I said, the first task is to convert this partial differential equation into the algebraic equation. So for that we have to convert this dou t by dou t and dou t by dou x, dou t by dou y, uh, or else you can also say dou square t by dou x square and dou square t by dou y square. Those things, how do you convert it into algebraic equation? So we do take advantage of the Taylor series approximation. Okay, and then we see for in Taylor series approximation you get t at say x plus h is equal to t of x plus f dash, uh, that, that is nothing but dou t by dou x into delta x, something like that. You get expansion. Okay, I'll not go into the depth of that. So basically from that you get an approximate for dou t by dou x. So you get it like t of x plus h minus t of x divided by delta h, something like that. I mean, you already are ignoring many terms, so those things are called as truncation error. So if you want to really get into these things, how do you come up with uh, this thing, uh, formulation for dou t by dou x in terms of just t at say I plus 1, I minus 1. So those are the grid points. So so in computational fluid dynamics, the basic aspect is that we are trying to resolve the domains into a number of points, at least in the finite difference method, and we are trying to find what is the solution at those points, the discrete points. Okay, so basically we have points, so I plus 1 in x direction or j plus 1 y direction, whatever you can call. So how do I bring up this equation in terms of that temperature at I plus 1? So using the Taylor series we can do that, but just let me come to the final formulation. If you want to understand the derivation, you can go through the lecture link which I'll give in this along with this video, and the mainly in the description I will give that. Okay, you can go through that video also if you want to understand how this will come up. Okay, so for example, if you want to find out dou t by dou x, it will be just uh, t of I plus 1 minus t of I divided by delta x. Okay, so that's just first order. Again, what is first order, second order? It all depends on what terms you are ignoring in that Taylor series. Okay, so that is how you get first order, second order, all those things. And this is forward difference. Now what is forward? Now you are trying to calculate this dou t by dou x at a point I, and you are taking the next point I plus 1, so you are going forward, so that is why forward difference. So similarly you have backward difference also. You want to get the values at I, you go to the previous value, you take it from the previous value, so that is what that is why it is written first order backward difference. Okay, and this is for dou t by dou x. Similarly you can do for dou square t by dou x square. Okay, all the order of this PD. Now there is one more approach. I said forward backward. You can do also a central difference. So if you want to find at I, you can take both I plus 1 and I minus 1. So that is called central difference. Okay, and central differences by default are like in second order, fourth order, or sixth order, something like that. You cannot get first order, third order, something like that. Okay, so the starting itself will be a second order thing. So what we typically do when solving these type of equation is that, see, if you have second order, that gives you more accuracy. So always we want to have more accuracy in our solutions. And also we don't want to go into too much of computational time by taking too much this I plus 2, I minus 2 and all also like that. Okay, so we just stick with the second order central difference, say for this dou t by dou x. Now sorry, for dou square t by dou x square, and then so that is the way in which you convert this dou square t by dou x square into t of I plus 1, t of I minus 1, something like that. Okay, so in the grid, in your whatever grid you are taking, so you can use this particular formulation for dou square t by dou x square. Okay, so that is how you get first dou square t by dou x square as t of I plus 1 minus 2 into t of I plus t of I minus 1 divided by delta x square. Similarly for dou square t by dou y square. Okay, so that would complete dou square t by dou x square and dou square t by dou y square. Now what else is remaining is dou t by dou t. Now you could also have done it using a central difference. Okay, so you could have taken, okay, here it's t, the denominator is t, so you have time. So time at I plus 1, so time at I plus 1 means time at next time step, it's actually t at n plus 1. So the next time, so for example, if you want to calculate at say I plus 1 itself, you know at I, so for example, you know at nth time step you are calculating at n plus 1th time step, so then you have to go to t at n plus 2 minus t at n divided by 2 times delta t. You can do that, but the problem is you don't know the value of uh, time a temperature at n plus 2. Okay, so that's the main problem here. So that is why we don't do a central difference, we do a backward difference. So for example, if I want to find the temperature at say n plus 1th time step, so what I do is I go back to the first order backward difference. So t at n plus 1 minus t at n, because I am finding at n plus 1, not n. Okay, so it will be t of n plus 1, okay, minus t of n divided by delta t. Okay, so that is how I do. And also you might ask one more question, what about these terms, at what time level they will be? So these are all spatial derivatives, okay, x, y, but you need to fix a time wherein at which time you are calculating this temperature. Okay, so we will be mainly talking today of explicit method. So in explicit method, we actually take it at the previous time step. So for example, if I am calculating the temperature at n plus 1, I take all these gradients at n at the previous time step. N is the previous time step. Okay, so you might be thinking that I am taking too many terms here. The first order central difference, sorry, first order forward difference, backward difference, central difference, and explicit, implicit methods, all those things. For a person who is already into CFD, these things, it will be very easy to grasp for them. If you are very new to CFD, what I would suggest is I will give some links of the video lectures at the description. You can watch those videos. Okay, those are my videos itself, which I have already recorded just for the theoretical CFD course. Okay, but my intention in this course is mainly on hands-on approaches, so I will not go into depth of these things. Okay, so okay, so please bear with me. Okay, now I'll just given it, but I will explain how these things are done. Okay, so dou t by dou t, you know how to discretize it. T at n plus 1 minus t at n divided by delta t. Okay, now you know also delta square t by delta x square. How do you do that? You also have come to know using this particular second order central difference. You have this particular formulation. Now when you do this at every grid point, okay, at every grid point whenever you do this, you end up with some algebraic equations. Now if you think here, when you do it using the explicit algorithm, so explicit means all these are at nth time step, and only here you get n plus 1. So you can see that you can solve it very easily. Okay, you can just take at LHS n plus 1 all the other term RHS n, and the values at nth time step, that is at the previous time step, those values you already know, right? So it's very easy. Okay, just simply write a code and solve it. Okay, you need not worry too much about this. But if you have an implicit algorithm wherein you take these also at n, okay, so all the temperatures you have at n plus 1, sorry, not n plus 1, so all the temperatures you have at the current time, which is n plus 1, where you want to find out the temperature, at that time the things will become little challenging, because you do not know the values at n plus 1, because you are trying to find them out, right? So at that time what you do is you solve it iteratively. So you will end up with equations like this: a t1 plus b t2 plus c t3 is equal to some constant. Similarly, for another grid point you will find again one equation. For the third grid point you will come up with third equation, something like that. Okay, so how do you solve these things? So one of the best way would be to convert this in terms of ax is equal to b system, and just get x is equal to a inverse into b. But we are running with too many number of grid points here. It will be like millions of grid points will be there. Okay, so you cannot do a direct inverse of a matrix like that. It will be very computationally inefficient thing to do. So the best thing here would be actually to solve them iteratively. So assume the temperature at n plus 1 where you are trying to find out. Uh, First, initially you assume it to be same as the temperature at nth time step, and then calculate T1, and similarly calculate T2. You know the updated value of T1 and T3. Okay, sorry, T3 you assume again at previous time step. Okay, so then you go to the next iteration. So within a time step you will have multiple iterations. Okay, so once between the two iterations, if the temperature gets steady, then you go to the next time step. Okay, so this is for only for implicit algorithm, which we will not do today. Okay, maybe in the next video we can do an implicit algorithm. Today we will just see an explicit algorithm wherein you don't know, wherein you don't need to do this. Okay, okay, so this is anyway extra, I would say. So we will try to stick with a basic explicit algorithm. So let us take this example case, a very simple example case, which I have obtained from my supervisor's textbook on CFD itself. So I'll provide the references at the end. Okay, so you can also look into what literature you can go through to understand more about CFD. Okay, so we have a square plate. Okay, there is no flow. Okay, this is just conduction problem, and we have a constant temperature at the west boundary, an insulation from the south boundary, and a constant heat flux on the west east boundary. So this should be QE east boundary, and then the convective boundary at the north. We have something like air which is flowing. Okay, it has some value of heat transfer coefficient and it has some temperature. Okay, assume it like that, some air is flowing over this square plate, and along the z direction it's a very long plate, something like that you can assume. It's like a so there is negligible heat transfer in the z direction. Okay, only we are concerned with two-dimensional heat conduction. Okay, so that's the problem statement. Now with this background, so whatever I have explained here, how to convert this dou t by dou t in terms of algebraic equation. Okay, so let us try to write the code. Okay, let us try to write the code from scratch. So that's the main intention of this course also. So I'll be doing this in MATLAB. So let me tell you, I think because many of the mechanical engineers do use MATLAB, not only mechanical, all type of engineers do use MATLAB, but people are more comfortable with this, and many people do use this, and it has some good features also, and you might be having a license of this. So if you want to do it in C or Fortran, you can follow the same logic, only the syntax will be different here and there. Okay, so whenever you write a CFD code, there are mainly three steps. Okay, first one is the pre-processing step. Even in the code development, I'm telling. Okay, the second step is the solution calculation, whatever you want to call it as. That is basically like running the simulation, what you do in commercial software. Okay, solution calculation. The third step is post processing, that is visualizing the results. Okay, so these are the main three steps. Okay, now pre-processing, what do? You define the domain. Okay, so let me define the length of the plate, the width of the plate. Okay, then what else, I need to divide this domain into some grid, right? So basically, let me pull up paint. Okay, So basically you have this square plate, something like this. Pardon me, this might not be perfect square. Okay, so we do divide this into number of grid points. This is mainly for FDM, finite difference method. Okay, so these are mainly our grid points. Okay, where these two lines are intersecting. Okay, the circles which I am drawing. Okay, and you already know what should be the value here. Okay, so this is the boundary grid point. These all these things which are there. Let me put it through some X mark, something like that. You already know these values. Okay, you need not worry about these values. Only these circles you have to find out. Okay, and you are doing this in MATLAB. So remember this I in MATLAB. So that's the first index in a 2D array. So you have an array. You can create an array in MATLAB. So it stores in this thing, row and column format. So this will be like your first index I, then the second index will be this columns j. Okay, so pardon me, it should actually be like this, j here and I here. Okay, I goes on increasing like this. Okay, so I will be starting from 1 to ny. Okay, ny is the number of grid points in the y direction. J will be starting from 1 to nx. Nx is the number of grid points in the x direction. Okay, so those are the values for nx. That is the way in which you define nx and ny. Okay, and yeah, so this should sum it up, and you divide this whole 1 to nx into equal number of parts called as del x, and 1 to ny in equal number of parts called del y. Okay, for the uniform grid which we are discussing as of now. Okay, so that's the fundamental thing. Let us try to write that. So lx ly is what I have written. Nx, let me take 21 grid points. Always it's good thing to take odd number of grid points. Okay, because then the number of divisions will be even, because the number of divisions will be n minus 1. Okay, so when you have like 5 points, it means that you will have 4 blocks. Okay, so that's the reason I'm taking it to be odd. Now how do I define del x? Lx divided by nx minus 1. Similarly, I will define del y as ly divided by ny minus 1. Okay, so the other thing is you also need to define what is del t. So in this equation, if you see, you have something called del x, del y, you have also delta t. So for that I might need the values of uh, this thing, the physical properties of the system. So that is again given in this particular slide here. So rho, cp and k. Okay, let me pull this up. Rho is equal to, what was the value, 7750. Okay, and cp value is 500, I guess. Yeah, and rho, cp and k 16.2. Okay, so what I will try to do is I will try to calculate something called as thermal diffusivity, which is nothing but k by rho cp. So what I will be doing here is then this thing I'll take it on the right hand side, k by rho cp. I can just write it as alpha. So that's the reason why I am defining k by rho star cp. And when we are doing an explicit algorithm, we cannot direct randomly take some value of delta t. Okay, so this is the thing which you have to keep in mind. Okay, so you are always, because if you take a too long time step, very high time step, what will happen is that you will miss the information being transmitted from left plate to right plate. Say for example, the heat is moving from left to right plate, and in 1 second it can only move say 0.1 meter, and you take the grid length of 0.1 meter, but you take delta t of 2 meter 2 seconds. So then you are just completely missing that information. Okay, you will not be able to capture that. So always in an explicit algorithm, you need to take care of some, you need to threshold the this thing, what do you say, the delta t, and that is thresholded by the value of alpha, because it is the diffusivity. So how fast will this move? Okay. Okay, higher is the diffusivity. You can sense this, right, physically, that whenever the diffusivity becomes more, the time step size should be less because there is a faster movement. So diffusivity will anyway come on the denominator, and lower is the grid size, lower should be the time step size also, because otherwise you will miss the information being transmitted from one grid point to the other. So we just have this del x square by alpha. You can also take uh, I think 1 by alpha into del x square plus del y square, whatever. But we usually can just take this also and just multiply it by zero point 0.2 just for safety, because we might end up with some divergence issues if you are exactly putting it at del x square by alpha. Okay. So this also derivation is already there in many of the literature, so I'll not go into the derivation. I gave you a physical sense. Okay, I think that should be good enough. Okay, so these are the things, and for boundary conditions, let us see if we need anything. Yeah, so we need h and t infinity, so let us also define that. H is equal to 100, t infinity is equal to 30. Okay, uh, and yeah, so this I think should be the pre-processing, and let us do some before initialization. I would say this will come in solution calculation only. Let us do some initialization of t. So t is equal to, what do you take for initial value? You can take anything, but better it will be if you disclose to the uh, physical reality. See, for example, at the west plate you have 100-degree, at right plate you have some heat flux, and t infinity is 30 degrees, so you can start with 30 degree, I would say. So 30 star. So once is formulation library which will generate a matrix with ones. Okay, so it's like 1111 of size ny comma nx. So that is why I have explained the logic behind ny comma x and x. So I will be the first this thing rows and then the columns. So in the in MATLAB, so it will be like ny first and then the nx. So it will be just having ones. So you just multiply it with a scalar value of 30. Okay. So we will also need a t new value. So this is like tn, and then we will also calculate tn plus 1, that is the new time step value, new time level value. So let us try to initialize that also, for starting with the same thing. Okay, so yeah, so this should be okay for initialization. Okay, so let us do now the time marching. So what we will do is we will solve this equation until and unless this the left hand side becomes 0, that is rho c into dt, dou t by dou t, it becomes 0. So what that means is that we are solving an unsteady equation, but we are seeing if the solution reaches to a steady state. So this problem will reach to a steady state, we know that. Okay, so we want to solve it till it reaches the steady state. So we create a parameter called as unsteadiness. Okay, so until this reaches to a very low value, we will keep on solving. So that's the logic. So initially we will set it to a very high value, and till unsteadiness is greater than 1 e power minus 6. So once it reaches below 1 e power minus 6 or some tolerance, whatever you want, we will close the simulation. Okay, so that's the logic. I hope you understand that logic. Okay, now you can directly calculate. Okay, so you can just go about. Okay, there are two ways again here. MATLAB has a an optimized way, but it might be a bit difficult for you guys, so I'll just do a basic looping of I is equal to, say, 2 to ny minus 1, because 1 is the boundary here. Okay, 1 will always be a boundary I. So 2 to ny minus 1, and then for j is equal to 2 to nx minus 1. Okay, Now I'll try to calculate T new of I comma j equal to T of I comma j. So that is what I am writing here, plus what is this, alpha star del t, because if you see this, it's nothing but uh, k, if you take outside, k by rho c will be alpha into delta t will go to the right hand side, okay, and dt will become t new minus t old, right? So that's why, and t old I have just put it on the right side. So I hope you can understand this. Okay, so del t star, so now I have to calculate this. Okay, t xx plus t yy is nothing but dou square t by dou x square plus dou square t y. Okay, okay, so that's it. So this is as simple as it can get, and then you can implement bc's here, boundary conditions. Okay, so those are the things, but main thing here is first I have to calculate txx, right? So how do I calculate that? T of I comma j plus 1, because j is for me x, okay, minus 2 star, that is the Taylor expansion which I have just showed, T of I comma j plus T of I comma j minus 1, okay, divided by del x square. Okay, similarly you can calculate del y also, ty sorry, but here you have to be careful, it's I plus 1, j will remain as it is, and here it's x. Okay, so you are done, that's it. So then you have to implement boundary conditions. So what do we have at the west boundary? We have a constant temperature, so that corresponds to so you have at the west, what do you have? You have the I value which is constant, okay, and you have sorry, you have j value which is constant, which is equal to 1, and you have I varying from 1 to ny minus 1. So 1 to ny minus 1, you can do it using a loop also if you find this a bit difficult. Okay, so what I have done is basically from I is equal to 1 to ny minus 1 and j is equal to just 1. Okay, so I'm setting the boundary condition, so it is equal to, I think, 100, right? The west boundary was at 100. Okay, yes, it's at 100. Now similarly, I would like to do for the east boundary and the south boundary. So east boundary will be nothing but this will be nx minus 1 to the east boundary. So it's k into dt by dx is equal to qw. Sorry, it's minus k dt by dx. You have to be very bit very careful about this signs. Okay, so it's nothing but minus k into dt by dx. How will you write? T at j plus 1 minus t at j. Okay, so you are already at the boundary, so this is j minus 1, because you are at the east boundary. Okay, you are already at the end, so you cannot have j plus 1 again. Okay, you are already at the east boundary here, this is the east boundary. So j minus 1 divided by delta x is equal to qw, but remember, qw, the direction is in the negative x direction, so whatever it is there here 10, it will be actually minus 10, and it's kilowatt. Okay, so minus 10 into 10 raised to power 3. Okay, 10 raised to power 4. So it will be like this. So let me just cancel out this minus and minus. Okay, so t, and then you are, what you are trying to write the code is for t of j, that is the boundary. So t of j, it will be equal to t of, sorry, this will be nx, huh? Not nx minus 1. Nx is the boundary, so nx minus 1. So what will it be then? This going to the right hand side, it will be 10 power 4 divided by k, right? So that's the way. k into dt by dx. Sorry, I missed del x by k. Yes. So t minus this t divided by del x, okay, into k. Yes, it should be equal to q. And then let us take one more easier boundary, that is the down boundary. What is this? This will be t. This is a south one, right? So here you just fix the I value, okay, as 1. Now the j is varying from 1 to nx here. Okay, that's the meaning. You can also write a loop here for j is equal to 1 to nx t of 1 comma j. You can write like that also. This is a optimized way, I would say. Okay, now what do you write? T of, this is nothing but t of 2, right? Because you are going up here you are looking from the, you want to calculate the value boundary here, you have to look up because you don't have anything down. Okay, so and also you are calculating t news here. Okay, these boundary conditions should ideally be applied for t new, t at n plus 1. Okay, here you are calculating. Okay, now the difficult boundary condition, I would say, because this problem has like all the boundary conditions which you can imagine, okay, for a transfer problem. So that is why I have selected this problem statement. It has insulation, it has specified heat flux, it has constant temperature, finally it has convective boundary conditions. This you have to be very careful. It's minus k into dt by dx. So at the top boundary you will have t of I plus 1. I, again I plus 1 you don't have. Okay, you just have I minus t of I minus 1. Okay, you have to go down because you can't go up here, so it's backward difference you have to do. Ti minus ti minus 1 divided by delta y minus k dt by dy is equal to h into t of I minus t infinity. Okay, so that's the way. Okay, so now you bring ti's all together on the left hand side and all the other things to the right hand side. So what it will become is, um, so ti will be having like a coefficient of, say if you send this minus to the right hand side, so it will be like k by delta y, and here you will have minus h, right? uh, or else yeah, you can do like that also, not an issue. K by delta y, and here you will have minus h. So that will be the this thing, but h later on you will bring it to the right hand left hand side, so minus h will become plus h. So all together it will become plus h only. Okay, so t new of the x index will be 1 to nx. Okay, y index will be ny. Okay, this is equal to, okay, this multiplied by this. Okay, multiplied by what? K by delta y, k by del y plus h upon h itself, right? Not upon something is not there. Okay, is equal to, what do you have on the right hand side? You will have this minus h into minus t infinity as h into t infinity, h into t infinity. Then you will have something else also, right? Something else from coming from here. So it will again become plus. Okay, plus t of, what is this? This will be value at the point below. Yes, this should be correct. Okay, and what will be the coefficient of that? Again k by delta y, k by del y. Now you cannot write this equation like this. Okay, you need to also send this because you are interested in this value t new. So you just send this on the right hand side, so it will go into the denominator. Okay, so that's the thing. So let me save it. I had already done this. Okay. Yeah, we should be good to go. Okay, I have not checked for the unsteadiness, right? Okay, you do all these things and then you calculate this unsteadiness value. Unsteadiness, because we have to check na, whether that is going to the bottom of thing or not, whatever it is. So what you do is you take the maximum of the matrix. So what you do is it's a 2D matrix, so 2 times you have to take maximum function, because it will do along one dimension only when you do max once. When you do absolute of t minus t new, okay, divided by del t, right? Okay, yeah, this should work. Absolute of t minus t new divided by del t, and whatever the row CPR. So if it goes below 10 raised to minus 6, it means that you are reaching the steady state. But what might happen is that in the initial time steps itself, there might not be a good amount of variation in temperature, because of which unsteadiness might go to a very lower value and you will get false convergence. So to avoid that, we will do something called as number of time steps. Okay, initially it will be first time step. We will also tell that, okay, the number of time steps should also be um, greater than 100. Okay, only till then you solve. Okay, if it is say if the unsteadiness goes below 10 raised to 6, but if the number of time steps is say less than 100, even then it has to solve. Okay, so that is the condition which we give. Okay, even if the number of time steps is less than 100, it will just keep on solving, because even though unsteadiness might reach a very low value, since the number of time steps is very low, it will keep on solving. Okay, so I'll just update the time step also, nt is equal to nt plus 1. So yeah, so that is how you do the calculation. Okay, so now maybe I think done with the code, we can just click on run. So so what will happen is that it will take a very small time step and it will do a lot of number crunching, which is going on here anyways. So just to speed up this thing. Oh, okay, we have not put the post processing part also. Okay, we have to first calculate the x values. And x y is equal to space 0 to L y n y. Okay, contour f and then x y comma t new. Okay. So this is a post processing. So contour f is the field contour through which you can visualize the temperature field. Okay. So yeah, I think this should be it. Mm, So we are not getting any error. So let us stop this program and check whether the values are initialized correctly or not. Yeah, delta t is coming to a large value here, which is actually good. Okay, and an x and y, and what is the t value? Let us also check what is the t value which it has generated. Okay, it's looks like it's not doing much here. Okay. So it has taken the initial this thing itself, initial time values. Okay, one more thing which I missed out here is the updation. So when you go calculate t new, and when you are going to the next time step, so what you have to do is that you have to also change the value of t is equal to t new. So it will be like going into the n plus 2, but you are still taking the n. Okay, so that won't help. So t is equal to t new is what you have to do. And Let us try to get the results first. Okay, let me just write it as something like 4 unsteadiness. Let us run. Yeah, yeah. So this is how you can expect. So I think what was there here? I don't know. Okay, so these are the temperature values. So you can plot the legend and all those things, but you can see here it is at 100. TW was at 100, and you are getting an insulated boundary condition. That is why you are getting a constant lines, straight lines here. So if you take the slope, that will be this thing, right? 0, because there is no change in the gradient. So insulation means dt by dx is 0. So that is what is being implemented. And here also you should ideally get some lines, that might be because of a number of levels. So it is a constant slope because the heat flux is constant here, so qw, right? So that's the way. So let us also try to increase the number of grid points so that we get a bit more good results, better results, I would say. Okay, and yeah, so okay, I think I have done some mistake here. Okay, it should be, what do you say? I think y is constant here. uh, okay, it's 1 to nx and ny, right? Yeah, so it's on the top, this thing, yes, right. I think the indexing was wrong here. Okay. Yeah, I think this is a better thing to see. Okay, because here you are getting constant slope because the heat flux is constant. Here you are getting zero slope because heat flux is zero. Here you are getting, I think, 100 as a temperature. Yeah, and since you are providing a heat flux here, you are seeing that the temperatures have risen. Okay, so that's the way in which you attempt this problem. Okay, I'll maybe attach this code also along with this video. You can maybe go through, first try to work on your own. If you have any doubts, you can refer to this code. And coming to the last part, that is the references. So these are the three main references which I would suggest for anyone, even for a beginner or someone who is already into CFD, for development purpose. This is purely for development purpose. Uh, First one is Hoffman and Chiang, which is like a basic book for finite difference method, because all these Taylor approximations, whichever I told here, the first order forward difference, first order backward, all these are given in Hoffman and Chiang. Okay, so this is the, I would say, the go-to book to understand finite difference method, and this is anyway a very popular book by Professor Patankar. And the third book is by my supervisor itself, but this book provides a very new insights into computational fluid dynamics. It gives the physical insight. So just as an example, I was telling, if you have some constant heat flux, you should be seeing slope constant, something like that. So it gives a physical intuition behind all this number crunching. Okay, so just if you are just interested in those type of aspects, you can also go through this book, and if you can contact me if you have any queries. Also, if there were any errors in this slides, please let me know in the comments also. Okay, okay, thank you.